pipeline. Immunology in Michigan, rattlesnakes, swimmer's itch, did a little bit of algal blooms, kind of covered the gamut. The tie-in though is climate change. I really want to know what happens. If you believe the environment is warming up, which I do, what's the impact on the cell biology? So really climate change and cell biology is my forte. Working a little bit with Rick on E. coli on the beaches, looking at a different instrument, but again, looking at E. coli in food crops and food processing centers. And I still play with climate change and coral reefs in the Gulf of Mexico. So if you ask me, is the world going to end because of climate change? And I tell my students, so I teach environmental biology in Allendale, and so my students often say, will the world end? And I said, yes, it will. Will it heat up? Yes, it will. How fast will it heat up? And I said, well, in about 100,000 to maybe 10 million years, we're going to have the same kind of climate that we have down on the equator, but I don't think you and I need to worry about that in a million years. Michigan has increased by roughly 2 to 3 degrees Fahrenheit per year, and we notice that we start to see, and you guys probably see, there's abnormal seasonal patterns going on. And all of it is related to, or not all of it, a lot of it is related to carbon. So we look at data that goes back to 1900, and we look at data, 2000, and we try to extrapolate that data and say what's going to happen in the future. We do know this directly related to carbon. If you don't do something to mitigate the carbon, there's a direct correlation. More heat, more carbon equals more heat. Lower the carbon, you're going to lower the heat. The problem with that, though, is when I tell my students when I teach this, if you have a small pot on a stove, very quickly to heat up the water, very quickly to cool down. If you have a pot of water the size of this room, long time to heat up, kind of like the Earth, take a long time to heat up. But if you snap a switch, it take a long time to cool down. And so those are the things you hear about environmentalists talking. You need to think about the future, and that's because it's going to take such a long time for everything to cool down. So we know that the warming is already having an effect. We see the migration. I call them Canadian geese, you call them American geese. We know that the migration patterns have changed for the geese population, for the goose population. We also know that there's a difference going on with the tulip festival and blooming. That's changed. There's a lot of indicators out there. I know some people say, yeah, but seriously, I believe in it, even though I'm a scientist and we talk about that. But I also farm. I grew up on a farm. My parents still farm. My family still farm. I farm out in Montague. When you had mentioned, hey, I live in Iris, I'm like, hey, so do I. I grew up in Iris. So we own our farm right here in Montague. And as a farmer, I'm telling you, there's something going on with the climate. For the seasonal warming, we definitely see, and if you look at 1970 to 2019, we see changes not only in the winter, in the spring, in the summer, and the fall. Again, there's something going on with the atmosphere. There's something going on with the water. As summers continue to become hotter, we expect reduced yields, potentially reduced yields in corn and soybeans. 70 years from now, Lower Michigan may experience 5 to 15 more days of each year where temperatures exceed 95 degrees Fahrenheit. It's a lot. It may seem like nothing for you and me. I tell my students as well, if I come in this room and I jack up the temperature by 1 or 2 degrees, you're like, yeah, whatever. But when we talk about algae and we talk about E. coli and we talk about other pathogens, those little bugs are saying, oh, bring it on, I love it, because it means massive reproduction for them. That's something we should be concerned about. And so, there's a number of different studies that show this extreme heat and say, we're worried about those extreme heat, hot days increasing over time. The greatest health concerns, unfortunately, are related to illnesses, which nobody wants to be sick. We're worried about waterborne illnesses, respiratory, and vector-borne diseases. Interestingly enough, Great Lakes Basin has warmed by roughly 1.6 degrees Fahrenheit, and we expect it to warm another 3 to 7 degrees in the next 70 years. I say 3 to 70. 70 is extreme. It really depends upon how much carbon we dump in the atmosphere. It really comes down to that. But a lot of studies have shown, again, Great Lakes and Lake Michigan are warming. We see, when I look at Canada, I look at the northern part of Canada, there used to be this huge ice gap that would cover up the north. That's gone. And now there's battles going on as to who has the shipping rights to move from one side to the other side of Canada, since there's no longer any ice there. Even the deep waters of Lake Michigan are warming at a rate of roughly 0.5 degrees centigrade or 0.9 degrees Fahrenheit per decade. Again, a lot. Not a lot for you and me, but for the small bugs, for the algal cells, for the food web, for the food chain, it's a big deal to warm up by that much. More than 70% of the total ice cover in the Great Lakes has diminished over the last 50 years because of that, I call it a pot of water, which is what Lake Michigan is. It's a pot of water that's slowly warming up. And again, I'll say it 1,000 times, the concern is if you could turn the light switch off, it's going to take a long time to cool down unless we make changes now. And there's a map that simply shows we do see decreasing ice cover in Lake Michigan. Increases in water temperature will allow warm water fish like bass to expand, but if you love trout, they're going to have to decrease. They're going to die out or they have to find another habitat to live in. As waters continue to warm, we expect again more algal blooms, more issues associated with fisheries, and degraded water quality. I use something, I don't know if I have time for this, but I'll see how this goes. I use an interesting instrument called imaging flow cytometry. Work coincides with what Rick's doing. Rick does a lot of DNA stuff in qPCR and cohort studies, and we're looking at in the studies that I've done with blueberries, for example, I'm looking at ag water, and we look at E. coli, for example. We're using this instrument called cytometry. Fancy instrument. Inside the instrument it has a bunch of laser beams. Ours has 4 or 5, but if you work at Pfizer, who studies, for example, COVID with the instrument, they have 12 to 14. The laser beams. So what is imaging cytometry? Number one, it has a camera hooked up to it. Anytime a cell passes through one of the laser beams, it gives you information of that cell. Flow simply called, refers to a fluid stream where the particle is in. Cyto talks about cell biology, and metry, refers to measurement. And so this kind of shows you that, here's a laser beam, cells passing through in a stream, and it reflects that light, and as it reflects the light, we get a bunch of different information. Everything we do is stained right now with DNA. So if I take an E. coli, if I take a Hab cell, if I take Listeria, or if I take Salmonella, we use a DNA probe, we get the DNA from that organism, we stain that DNA so that when it sees a cell in a solution, it binds to the DNA, it's fluorescent when it hits the laser beam, and we get all kind of cool information. And so this is an interesting chart. In this case, for example, we can see the chromatin, we can see the DNA, we can see the protein, we can see what's on the surface, we get a lot of information. Sometimes they say too much information is horrible. Well, we want as much information as possible so we can predict what's going on. When I talk about this in class, people are like, it's a ball of dots. What does that dot mean? Who cares what's there? And so, again, explain this further. Each of those dots represent, for example, a cell. When we look, because the instrument has a camera on it, we can actually look at and characterize each of the cells. In this particular case, that group of cells represents natural killer cells. In this case, this study was looking at immunity, how climate change and heat stress affected immunity in rattlesnakes. And so we're looking at, what does it do to the cells? We can look at natural killer cells, look at white blood cells. We have nice pictures of red blood cells. We can count them. We can look at which ones are dying, which ones are alive or healthy. We're looking at lymphocytes. We're looking at, I can barely see what happens when you get on my age. We look at monocytes. And then in the background, you'll also use beads. Beads are always running in the background to help us characterize the number of cells that are there. So for every one bead that passes, we can characterize the number of cells that are also passing. There's a lot of information there. So depending upon how and what you're staining the DNA with of the particular target cell that you're going after, you can look at DNA damage, you can look at stem cell stuff. I've used it for ocean sciences, looking at corals. You can look at cell-cell interaction. There is a lot of information that comes from that. And so we're trying to piggyback with Rick and saying maybe there's an additional instrument that might be helpful or useful when we look at pathogens anywhere in Michigan. And so that's my last slide. It says, hey, have any questions? I know we're going to wait because we've got one more to go. And there we are. I thought it was funny. My son found that for me. And I was like, yeah, I wouldn't answer that question either. Got it? Being stubborn?
No, I just didn't open my mouth.
There you go. So we're saving the best for last, and I'll get out of here.
Oh. Don't leave the hype. All right, well, my name is Carlos Calderon. Whoa, did I don't know. I think we just lost the. I don't know if you did or not. Did my computer shut down?
No, it's